Good morning, everybody. So today we're going to have our first lab session on implementing optimal control problems. So I think it's going to be a good one for you. The idea is to follow the notebooks that I've pushed on the repo on Friday. So you should update your Arc repository running either a git pull command on your existing repository or cloning the repository from scratch, whichever is easier for you. In case you don't have Jupyter Notebook installed, you can also use the scripts that are in the same folder as the notebooks. They're not going to be exactly the same as the notebook, but very similar, so it shouldn't change much for you. But well, installing notebook is pretty easy. It's pip install notebook. It's a command I told you to use on Classroom. So all the files are going to be in the folder optimal control, Casadi, Adam. And the notebooks are the files ending in IPyNB, like intro to Casadi with collocation, that's a notebook. And the other files ending with .py instead are the standard scripts. So more or less what we are going to do today should be, well, the intro to Casadi and then manipulator collocation and manipulator shooting, these three notebooks, if we have enough time. And if you don't want to use the notebooks or you can't, you can use directly the Python files, which are joint space collocation and joint space shooting, which are pretty similar to the notebooks. So I'm going to use the notebook. So to start the notebook, you need to run the command Jupyter Notebook from the terminal. You run it, and it should open a browser window. Yeah, we shouldn't have been here. So that's the window should open. And then you look for the folder Arc, optimal control, Casadi Adam, and here you have the notebooks. We're going to start with this intro to Casadi with collocation, because this is just to get started a bit with the library Casadi, which is the main library we're going to use to solve optimal control problem. So the idea for this first notebook is just to implement a trajectory optimization problem for a simple robot model using collocation. So as a reminder, this is the standard formulation for a discretized optimal control problem. So the variables of the problem are the state trajectory X and the control trajectory U. This is collocation, so both state and control are decision variables. We have a running cost, which is a simple summation in discrete time. We have a terminal cost, which depends only on the terminal state. And then we have a bunch of constraints. First of all, we have the dynamics constraints. We might have inequality constraints on state and control. And then we have an initial state constraint, because typically the initial state is fixed. It's not mandatory. You can also have problems with a free initial state, but most cases you don't. Then we need to discuss a little bit how we model the robot manipulator, so define what the state is and what the control is. Since we're going to start simple in this first notebook, we decide that, well, the state is, of course, the joint positions and the joint velocities. That's always going to be the case for modeling a robot manipulator. But for the control inputs, instead of using the torques, we're going to use the joint accelerations. So the dynamics is a simple double integrator, and it's a bit easier to begin with. And now we can start introducing Casadi. So Casadi is this amazing library that makes formulating nonlinear optimization problem in Python extremely easy for you. and me. And it also takes care of all the algorithmic differentiation, which otherwise we would need to take care of, and it's a pain. So basically, thanks to Casadi, we can formulate the optimization problem in Python with a very user-friendly API. And then we don't need to worry about computing gradients and Hessian of the cost function or the Jacobian of the constraints, because that's all automatically done by Casadi, and also in an efficient way using automatic differentiation techniques. So it's efficient and is kind of for free. The only limitation is that you need to be a bit careful in how you formulate the cost function and the constraints, because since this stuff needs to be differentiated, well, you can only specify differentiable functions. That goes without saying. So the objective for this first notebook is to implement the following optimal control problem. Let's break it down. We have a running cost, which contains 3 terms. We have a penalty on the distance between the desired joint configuration, QD, and the current joint configuration, QK. So K represents the time step. Then we have a penalty on the squared norm of the joint velocities. We don't want the joint velocities to be too large. We have a penalty on the control inputs, which are the joint accelerations in this case. And then we have a terminal cost on the joint distance between desired and final joint configuration. And then the constraints are simply the dynamics. The first 2 equations are the dynamics, which is a double integrator. So basically, the joint positions are the integral of the joint velocities, and the joint velocities are the integral of the joint accelerations. As simple as that. And we have a fixed initial state. So that's the problem we want to formulate. This is kind of the easiest optimal control problem we're going to deal with. And then starting from this, we're going to make things more and more complicated. How are the constraints of this problem? What form are they? Yeah. Linear, yeah. So this is a problem with linear constraints. And what about the cost function? Quadratic, yeah. So this optimal control problem is actually a QP. So it's the simplest optimal control problem you can imagine. So it's convex, and it doesn't even have inequality constraints at the moment. So if everything goes according to the plan, this should be solved with 1 iteration of the solver. So super fast. So let's start implementing. Well, just looking at the implementation because it's already implemented. This first segment, it only contains the hyperparameters of the problem. So we define the size of the control input, the size of the joint space and Q, and those are 3. The size of the state space, which is twice, because we have positions and velocities in the state, so you have twice the size. So it's going to be 6. The length of the horizon, so number of time steps, I set it to 30. The duration of the time step is 10 milliseconds. Initial state, I simply set it to 0. So this np.zeros is a function of the NumPy library for creating an array containing all zeros. The desired joint angles, I simply randomize it. So I use this function rand, which generates a random array of size and Q. And all the numbers are going to be between 0 and 1 using rand. And then these are all the weights for the cost function. So the weights on the position error, the velocities, the accelerations, and these are the weights on the final cost. Actually, the final cost contains both a terms on the position and a terms on the velocity, but it didn't show in the last slide because I think it didn't fit the screen. So it was going outside. Oh no. Yeah. Okay, so it was there, but it didn't fit the screen. So when I visualize it, it doesn't show, but it's there. So here I'm simply defining all the parameters. And here we start really creating the optimal control problem. So everything that's going to happen in Casadi is going to go through an object of class opti. So Casadi is imported as CS, it's just a shortcut. So we create an object of class opti, and that's going to be our API for formulating the optimization problem. So we create it, and then we use this function here. It's actually a method, opti.variable, for creating a variable of the optimization problem. And we can call it how many times we want. Every time we call opti.variable, a new variable is going to be added to the optimization problem. So what we do is that we call it once for every state variable and once for every control variable, specifying the different size, of course, of state and control. And we store all the resulting optimization variables in these two lists, capital X and capital U, which are lists that contains all the states and control variables. So this is something that we're going to do always, basically, when defining an optimal control problem. And of course, we do that both for the state and the control, because here we are aiming to achieve a collocation formulation. So both state and control are decision variables. If it was a single shooting, we would only do it for the control, because the state wouldn't be a decision variable. Yeah. The method opti.variable is creating a decision variable for the optimization problem. Basically, defining an optimization problem boils down to defining the decision variables, the cost function, and the constraints. So we're going to follow basically these three steps. But the first step needs to be creating the decision variables, because the cost function and the constraints are going to be functions of the decision variables. So the starting point is always defining the decision variables. Actually, here we are not doing anything. We are just defining a function that creates the decision variables, but we haven't called this function yet. We're going to call it later. And this function takes as inputs the horizon size, so capital N, the state size NX, and the control size NU. That's all it needs. And then we have instead another function that defines the running cost and the dynamics. So for defining a constraint in the optimization problem, there is another method that we need to use of the class opti, which is called subject2. I think it's a pretty clear name. So when you see opti.subject2, what you're seeing is the definition of a new constraint. It can be either an equality constraint or an inequality constraint. You're always using the same method, subject2. If it's a equality constraint, then it needs to be defined with a double equal operator. Don't use the single equal operator, because I don't know what it does, but not what you expect. So this is simply the definition of the initial condition. So we are saying that the state at time step 0 should be equal to x init, which is the parameter we have defined above, defining the initial states. So in particular, in this example, x init was simply 0. And then we start a for loop over the horizon. So this is going from 0 to n minus 1. And for each time step, we define the cost function, so the running cost, and the dynamics constraints here in the last two lines. So let's take a look at the cost function first. Cost function is composed of three terms. The first term is measuring the distance between the desired joint configuration, QDES, and the joint configuration at time step k. So here what's going on is that I'm taking the state at time step k, so xk, but the state contains both positions and velocities. And here I only need to measure the distance in the position space. So out of this like 6-dimensional vector, I need only to take the first three elements. And that's why I'm using this notation, because NQ is the size of the joint space. So I'm taking the first NQ elements of this vector. And then computing the distance with respect to QDES. And then I take the square norm of this. And one way of taking the square norm of this is to multiply this vector times itself. So if you take a row vector by taking the transpose, dot t takes the transpose of a vector. So normally the vector would be a column. You take the transpose, it becomes a row. You multiply times a column. Row times column gives you a scalar, which is what you want. I'm using the slice because the state contains positions and velocities, and here I only need positions. So I need to take the first NQ elements of the vector. K is a time step, yeah. So capital X is a list containing one element for each time step of the horizon. So when you do xk, it means the state at time step k. And then I multiply times the time step. Actually, this is almost useless because I'm multiplying everything times the t, so it's just a scaling factor over the cost function, just to simulate what would happen with a continuous time integral, basically. But I could also not do that, it wouldn't change anything. And this term of the cost function is scaled by the weight WP, which I defined above. And then I have other two terms. This one is for the velocities, because you can see that I'm taking the state at time k, and then I'm using the slicing operator, but for taking the last NQ elements of the state vector. So those are the joint velocities. And here I'm simply multiplying the joint velocity vector times itself to have the squared 2 norm. Because I want to penalize velocities no matter if they are positive or negative, I take the square. Same thing goes for the joint accelerations, which are my control inputs. In this case, I don't need to apply any slicing because U is simply the joint accelerations. So I take the whole UK and square it. For doing the multiplication between NumPy arrays, I need to use the at symbol. I think we already went through this, but just to reinforce. So the cost is initialized at 0, and then at every iteration of this for loop, I add these 3 terms for every time step. So at the end, I have basically the summation of the 3 terms over the whole horizon, which is what I wanted to achieve for my running cost. And then I need to specify the dynamics as a constraint. So I'm going to use again the method subject to. I'm going to use the to equal operator as above for the initial conditions. And here I'm saying that my joint positions at time step k plus 1 is equal to my joint position at time step k plus dt times my joint velocities at time step k. And the second line instead says that my joint velocities at time step k plus 1 is equal to my joint velocities at time step k plus dt times the control input, which is the joint accelerations. Are we good? And now the only missing part is the terminal cost, because we only defined the running cost. The terminal cost is very simple. It's basically the same thing as the running cost, but without the penalization on the joint accelerations. Because the terminal cost only depends on the state, it doesn't depend on the control inputs. So you cannot have a penalty on the control inputs for the terminal cost. Here, to make sure that I take the last element of my state list, I use the operator, the index -1, which always takes the last element. When you use negative number, you start from the end of the list and you move backwards. So -1 is the last one, -2 is the one before that, and so on. And I'm using the different weights, WP final and WV final instead of WP and WV, because I have different weights for the terminal costs than for my running costs. I forgot to execute this one. Okay, so now I'm simply calling all the functions that we just defined, because I didn't call the function yet. So first I'm calling the function create decision variables, which gives me the list of state and control variables. Then I'm calling the function define running cost and dynamics, which gives me the running cost. Then I'm calling the function define terminal cost, which gives me the terminal cost. And then I'm calling the function opti.minimize to say this is the cost that you should minimize. Because so far I had only created the cost, but I didn't specify the cost to the optimization variable. So opti, which is the object that is containing all the information regarding my optimization problem, at the moment was not yet aware of the cost function. It becomes aware of the cost function when you call opti.minimize. So basically there are 3 methods of opti that you need to work with. Opti.minimize to specify the cost function, opti.subject to specify the constraints, and opti.variable to create decision variables. You only need to remember these 3 methods. So it's a very lightweight API. It's almost as writing the math, basically, on a piece of paper. So we execute this, everything works fine. Now that we are done defining the problem, we need to define the solver which is going to try to solve the problem. And actually, Casadi is solver agnostic, meaning that you can use Casadi with different optimization solvers, which is a very nice feature. So the same codes that you write for using a certain solver, you can also reuse it when you switch to another solver, in case the solver that you have been working with in the past is not sufficiently powerful for you, you need to change. Well, you just need to basically change these two lines here in your script, and the same code is going to work for a different solver. By default, Casadi is shipped with the IP-opt solver, so you already have it installed on your machine when you install Casadi, which is a pretty powerful optimization solver that deals with sparsity in the optimization problem. So it's going to work very well for collocation, which is a sparse optimization problem. So this is how you create the solver. You call opti.solver, you specify the solver name, which is IP-opt. And if you want, you can specify parameters to pass to the solver. In this case, I'm not doing it because you can see that this opt object is not used. This part of the code is commented. You can use it when you want to remove all the stuff that the solver prints when solving a problem. So since this is the very first time that we use this solver, I think it's nice to take a look at what the solver prints, just so that you get acquainted with it. But in the future, we are going to suppress all the prints because it's a bit annoying. It prints a lot of stuff. So if you want to suppress the prints, you basically just remove this comment here. And so you suppress the print by specifying these options. So you set basically print level to 0 and print time to 0, and that removes all the prints. But for the very first time, we're going to keep all the printing. And so when you call opti.solve, so actually here you're seeing the output from the last time that I called it. Now I'm calling it again. You can see that it prints lots of stuff. So opti.solve, of course, is a method for solving the problem. We cannot see everything, so I'm going to switch to the standard notebook GUI. Well, first of all, it just prints this advertisement saying, okay, you're using IP-opt, which is a library for large-scale nonlinear optimization. This is going to be printed the first time that you call the solver in every script or notebook, but then when you call it again, it doesn't keep printing it. Then it tells you something about which IP-opt version you're using, which linear solver you're using, and then it starts printing information about the optimization problem. So the number of non-zeros elements in the equality constraint Jacobian, the number in the inequality constraint Jacobian, which is 0 in our case because we don't have any inequality constraints, and the number of non-zeros in the Lagrangian Hessian, so 266. Is that a lot? So how many elements should the Lagrangian Hessian have in our problem? I don't know. I didn't do the math yet. So let's think a moment about it. The state variables have dimension 6, and I'm making 31 of them. Okay, so it's 31 times 6. And then I have 30 control variables of size 3. So 30 times 3. So it should be n plus 1 times nx. plus n times nu. So that's the size of my decision variable vector. A number of decision variables. And then number of elements of the Hessian. Well, I need to take this and var. The Hessian is a square matrix with size equal to the number of decision variables. So the number of elements of the Hessian is simply n var to the power of 2. So my Hessian has about 76,000 variables. Okay. So out of these 76,000 variables, the number of variables that is not 0 is less than 300. So that's how sparse the problem is. You can see that the vast majority of the variables in the Hessian, of the elements of the Hessian, is 0. Because I have only like 300 out of 70,000 non-zero variables, which is very good news because it means my problem is super sparse. So that's the number of variables, which should be the same. Yeah, it's the same that we computed, 276. I didn't see it was printed. Number of equality constraints, and then it shows basically what happens at every iteration of the solver. And you can see it only did one iteration as expected, because this is a QP problem, so it can be solved in just one iteration. And for every iteration, it shows the objective, and then it shows alpha, which is the line search parameter that we have seen when discussing the line search. And you can see that alpha was set equal to 1, which is good news. It means it took a whole Newton step. And then you have here all these values that should be very small when the solver converges. And indeed, they are very small. They are basically the numerical errors on the convergence thresholds and the constraint violations. So they are like 10 to the minus 16. So that's very good news. And indeed, it says number of iterations, 1. And then it prints a bunch of other stuff. It tells you how many times it evaluated the objective function, the gradients of the objective function, the equality constraints, the Jacobian of the equality constraints, and the total time it took to solve the problem, 8 milliseconds. Well, it's a very simple problem, so it's reasonable that it can solve it very fast. Okay, so now we have the optimal solution to the problem, which is hidden inside this object called sol. So we need to do something with that. How do we extract the solution? Well, there is this method which is called value. So you can call sol.value and specify a decision variable, and that gives you the value of that decision variable at the optimal solution. So here is how we recover the whole state trajectory. We just do a for loop. This is called a comprehension list. It's just a way to do a for loop in one line in Python. So I'm using k going from 0 to n. And for every value of k, I'm recovering the value of the corresponding state variable, xk, using this sol.value method. and I'm putting everything. So that would normally give me a list. This would be a list. And then I'm calling the function np.array to transform that list into a NumPy array. So it's just easier to work with. And I'm taking the transpose just because I like it better in one direction than in the other one. So I'm doing the same for both for the state and the control. And then again, for convenience, I'm splitting the state array into the joint configuration array and in the joint velocity arrays. So it's a bit easier to work with when doing the plots. So I'm taking all the columns of X, but I'm taking only the first NQ rows, which contain the joint angles. And instead, I'm taking the last NQ rows when getting the joint velocities. And this is just some code for doing plots, basically. Here, I'm going to plot the joint positions, the joint velocities, and the joint accelerations. So to see them, I'm going to exit here. So I'm going to see 3 trajectories because I have 3 joints in this example. And you can see here, these dotted lines represent the desired values for the joint angles, which were randomly generated. So they're just random numbers between 0 and 1. And you can see what the joint angles are doing. They are starting all from 0, and they're moving towards the target. They don't reach the target, which is fine. Because that was not a constraint. I just had a cost on reaching the target. Why do you think they don't reach the target? Yeah. So I have different terms. I have a penalty on reaching the target, but I also have a penalty on joint velocities being small and joint accelerations being small. So the solver is actually trying to reach a compromise between these 3 objectives, which are not compatible. Because the optimal thing for minimizing joint velocity and accelerations would be 0 acceleration, 0 velocity, I just stay where I am. But that's incompatible with reaching the target. So we have 2 conflicting objectives, and the solver is achieving a trade-off between these 2. So these are my joint angles. These are the joint velocities. They start from 0, they grow, and then they go to 0 again. And these are my joint accelerations. They start positive, they decrease, they reach 0 about here, and then they become negative and they end negative. Because first you accelerate and then you decelerate to have 0 velocity again at the end. So if we wanted to be more precise with our final state and reach the desired joint angles, we should go back here and we should play a bit with these weights. What would you change? We have 5 weights: WP, WV, WA, and then WP final, WV final. P final, how much? 10. Okay. So if you want to re-execute all the notebooks, you can do kernel, restart, and run all. So now the desired joint angles are different because they are randomized. So every time you execute, you get different values. But we can see that now we are much more accurate in reaching the desired configuration. Apart from that, the other curves look more or less the same. Okay, I don't want to spend too much time on this notebook because this was just to get you started, to get acquainted with the API of Casadi. But this is not really an interesting optimal control problem to play with because it's much simpler than what we want to do. Okay. So this was just so that you know the main methods and functions of Casadi, so that when we move on to a more complex problem, you're already familiar with the API. So I suggest we don't waste more time on this and we move on to the next one, which is going to be more interesting, and that's manipulator collocation. So here we're going to try to do kind of the same thing, but for a robot manipulator. So it's going to be more interesting. And still we're going to stick to collocation for this notebook. The next one is going to be instead using shooting. So now, since we really want to do the problem for a robot manipulator, the key difference is that we cannot simply model the robot as a double integrator, because a robot manipulator is not a double integrator. You cannot directly control the joint accelerations. Your control inputs would normally be the joint torques, because that's what the motors produce. They produce torque. So we're going to say that U is equal to tau. Then the dynamics of the robot, well, we know it. The dynamics of the robot, well, we normally write it down as m q double dot plus h equal tau. But now we need to write it in the forward dynamics form. So we need to express the joint accelerations as a function of the state and the control inputs. So I simply move the h term to the right-hand side, and I multiply everything times m inverse. And this is my dynamics. So q double dot equal m inverse times u minus h, where u are the joint torques tau. So this is the forward dynamics of a multi-body system. And then using these formulations, the joint torques are simply bounds on the control inputs. So they're very simple.
Could you repeat why we have to offer one?
Because in the standard formulation of an optimal control problem, you need to have is x dot equal f of xu. Okay, when we work in continuous time. So x dot, what it means for a robot manipulator? Well, x is q dot. So x dot is going to be q dot, q double dot. So we need to have an expression which says q double dot equal to something. And so that's what I did. So I need to move everything on the right-hand side so that on the left-hand side, I only have q double dot. It's just to put it in standard form. But it's the same equation, basically. So this would be the standard way of modeling a robot manipulator in an optimal control problem. However, there is an alternative way, which is instead of assuming that my control inputs are the joint torques, I could still assume that my control inputs are the joint accelerations, even if they're not in practice. It's just a modeling choice. And if I do that, my system dynamics is a double integrator, as in the example we just went through. So the system dynamics become super simple. But then how do I ensure the torque bounds? Well, I can recompute the joint torques using my dynamics. Because if you are my accelerations, then my joint torques can be computed using this expression. M times Q double dot, which is U, plus H. This gives me the joint torques. And then I can have inequality constraints on this expression, saying that this expression should be between tau min and tau max. And this expression here is what is typically called inverse dynamics, because it's just the inverse operation with respect to the forward dynamics, which we just described. So inverse dynamics, we go from the accelerations to the torques. Forward dynamics, we go from the torques to the accelerations. Those are inverse operations. So to recap, we have two choices for modeling the robot manipulators in an optimal control problem. We can either do like the straightforward thing, which is assume that my control inputs are the joint torques. And in that case, we get a nonlinear dynamics for the robot, which is based on the forward dynamics. And we get simple bounds for the torque limits. The alternative choice is to assume that my control inputs are the joint accelerations, even if in reality they are not. And in that case, I get linear dynamics, but nonlinear inequalities for the torque bounds based on the inverse dynamics equations. So I'm basically moving the complexity from the dynamics to the inequality constraints. But the complexity is always there. It didn't disappear. So it's no magic. I'm just moving things around basically by changing my definition of what the control inputs are. And these two formulations are mathematically equivalent. So they both represent the same system, the same constraints. I'm not losing anything in mathematical terms. So how am I gonna choose which one is best? Well, I'm gonna do it based on computational cost. It turns out that the inverse dynamics is actually more efficient to compute than the forward dynamics, despite what the name would suggest, because typically forward operation is more efficient than an inverse operation. But in this case, actually, the inverse operation is more efficient than the forward operation. So when you call this function in a library, well, it's faster to call the inverse dynamics than the forward dynamics. So just for that reason, in general, it's more convenient to rely on the second model than on the first model. And on top of that, we have a second reason why it's more convenient for us to use the second option, is that the library that we use for modeling the robot dynamics, it doesn't implement at the moment the forward dynamics. So even if we wanted to, we couldn't really use that. So we need to rely on the second option for two reasons. And well, everything I just said is just written down there for your future reference. So the library I was talking about is called Adam, which is a very unfortunate name because it's a name of a much more famous algorithm for optimizing neural networks. It has nothing to do with that Adam, it's just happened to have the same name. Okay, so now that we have decided that we are going to stick to using the joint accelerations as our control inputs, we can write down the formulation of the problem. It's very similar to the formulation we had before, but we have a few extra pieces here and there. So first of all, in the cost function now, we are using this y function, which is just a function representing the position of the end effector of the robot. So it's my forward geometry function. That's because I typically want to have my cost function depending on the position of the end effector rather than on the position of the joints. It's much more convenient to do that. So here what I'm doing is I'm penalizing the distance with respect to a desired end effector position, yd. Then I have my usual penalties on the joint velocities and on the joint accelerations. And then I have a terminal cost. Well, it's not completely shown because it doesn't fit in the screen, but you can imagine it's the same as the running cost for the joint positions and joint velocities without the term on the joint accelerations. Then I have my dynamics, which is a double integrator as before. I introduce some inequality constraints for the joint angle limits, the joint velocity limits, and the torque limits. And the torque limits are complex inequality constraints because they use the inverse dynamics function. So the robot dynamics model enters here in my joint torque constraints. And then I have a fixed initial state as usual. So that's the optimization problem that I want to formulate, which you can see as an extended version of the problem we worked with before. Well, this is just all the libraries that I need to import. The main new entry is this one, which is Adam, the library I just mentioned. That's the library that we're going to use for modeling the robot, both in terms of kinematics for computing the position of the end effector, and in terms of dynamics for computing the inverse dynamics. Apart from that, everything else is kind of already known. Here I'm loading the robot model. The robot I'm using for this example is always the usual UR5 robot, but the script is actually pretty general. So you should be able to work with a different robot model by changing this line here. So you can change the robot name with a different one. And well, of course, then a few things here and there, like the initial states, the desired and effector of position, you might need to change it. But apart from that, everything else should be working for any robot system that you want. Here I have a bunch of hyperparameters, like the time step duration. I set it to 20 milliseconds. Number of time steps is 75. Initial state. And here, this is one of the few lines that you will need to change if you change robots. It's the name of the end effector frame of the robot. So that's robot dependent. So the robot model is represented by a sort of XML file called URDF. And inside that file, each link of the robot has a name. So basically here you need to specify what is the link that you want to use as end effector in your robot. And in this case, it's called EE link, which stands for end effector link. And here I have my desired end effector position, which is a 3D vector, XYZ. Then in this case, I'm using a slightly different way of defining the dynamics. It's just to show you that there are different ways of doing stuff in Casadi, which may be more convenient depending on how you want to structure your code. You could still use the old ways, which is, I think, simpler to digest. But this was the old version inside Casadi for defining variables, which can also be used today. So this is a way to define the dynamics as a double integrator. That's not very important. Here, interesting stuff. Here is basically where we are using the Adam library to define the model of the robot in a way that is compatible with Casadi. So everything goes through this object, which is called kin-din computations, so kinematics and dynamics computations. This one takes the model of the robot as a URDF file, so robot.urdf, and you can specify the list of joints that you want to consider. So you may work with a subset of the joints of the robot if you want to. For some reason, maybe you don't want to use some of the joints. That's especially useful if you have a very redundant robot like a humanoid. You maybe want to work with a subset of the joints to make the problem a bit simpler. You can do that by specifying a subset of the joint list. And then here we are basically defining the inverse dynamics function. And to do that, we are going through two functions. One is the mass matrix function, and one is the bias force function. So those are the function for computing the mass matrix M and the function for computing the bias forces H. So I am creating these functions here, and then I'm calling them here. The notation is a bit more complex than it would need to be for a robot manipulator because it is thought for mobile robots. So robots that have 6 extra degrees of freedom for representing their configuration in space, so because they can move around. So you need to specify also the configuration of the base of the robot and the velocity of the base of the robot. So the velocity is a 6-dimensional vector for linear velocity and angular velocity, and the configuration is a 4x4 homogeneous matrix. In this case, since the robot has a fixed base, is a manipulator, I simply set them to their default value, which is 0 for the velocities and the identity for the homogeneous matrix. And I need to pass this information to these functions. And also the output of this function has 6 extra elements at the beginning, defining the mass matrix and the bias forces for these 6 extra base degrees of freedom, which I need to remove. So I'm using again the slice operator to remove the first 6 elements from the bias forces and the first 6 rows and 6 columns from the mass matrix. So what I get here is the bias forces and the mass matrix for my robot manipulator without these 6 extra degrees of freedom. This is just because the Adam library was thought for mobile robots and not for fixed robots. Now, once I have M and H, I can simply do M times Q double dot plus H, and that gives me tau, which is my basically inverse dynamics function. And I can define this as a function in Casadi using this notation, Casadi.function. I give a name to this function. I specify the inputs to the function, which are the state and the accelerations, and the outputs, which are the joint torques, tau. So later on, I will be able to use this function in DIN when specifying constraints inside my optimization problem, because this is a Casadi function. I run this and move on to the next. Here I'm checking that the name of the frame that I specified above really exists in the robot model. This is just a sanity check. Of course, if you use my name, it's gonna exist. But in case you change it, this is checking whether that name exists in the robot model. And then I'm using the forward kinematics function for computing the position of the end effector which is going to be useful when defining the cost function for the optimization problem. So same thing basically as before. I need to specify also the position and orientation of the base of the robot, even though it's a mobile, it's a fixed robot, so it's simply the identity matrix. This is going to be called FK, which stands for forward kinematics. Here I'm recovering from the robot model the position limits for the joint angles and for the joint velocities, and I'm transforming them into list and concatenating them together to define the lower bounds for my states. And I'm doing the same to recover the torque limits, tau min, tau max. So all the limits for the joint angles, joint velocity, and joint torques are specified in the robot model. So this URDF file. So I don't need to specify them manually inside the script. I simply read them from the URDF file. So when you switch to a new robot model, automatically all these limits are updated. And now we're going to do something that's very similar to what we did before in the first notebook. So we're going to go through the usual step of defining the decision variables, defining the cost function, defining the constraints, so that we have our optimization problem. The only difference with respect to before is that now we also have inequality constraints on the state. So my state variables are going to be bounded. So I'm going to use, as usual, the method subject to specify constraints. But now I'm using it in combination with this other method, which is bounded, which is useful for specifying bilateral bounds on some variables. Okay, so since I have both lower limit and upper limit, I can specify both of them in one line using this bounded method. So I'm saying that my state, the last state that I added to the list, is bounded between an upper bound and a lower bound. I don't do the same for the joint accelerations, because the joint accelerations don't have a bound. Only the positions, the velocities, and the torques have a bound, not the accelerations. Here I define the running cost and the dynamics. So the main difference with respect to the previous script is that my cost on the positions actually depends on the end effector position, not on the joint positions. So I need to go through my forward kinematics function to compute the end effector position here. And then I compute the error between the end effector position and the desired end effector position. My dynamics, well, it's my double integrator dynamics integrated with an Euler scheme. So a very simple numerical integration. And here I have my torque bounds. So all the robot dynamics goes in this expression here. I'm using the inverse dynamics function, which I defined above, which takes as input the states and the accelerations, and it computes the joint torques. And I'm specifying that these joint torques should be bounded between tau min and tau max. And I do that for every time step. Here I define the terminal cost, which is nothing special. It's just the same as the running cost, basically. And here I'm using the functions that I just defined above for creating the decision variables, defining running cost and dynamics, defining terminal cost. And then I say to my opti object that this is my cost I want to minimize. It's a summation of the running cost plus the terminal cost. I create the solver. Here I specified a couple more options for the solver, especially these last three ones, which define the convergence thresholds. So you can specify to the solver how accurate you want it to be. Of course, the less accurate you want it to be, the faster the solver is going to converge. And here I'm using quite generous tolerances, so 10 to the minus 4, so that the solver converges faster. I think by default, they should be 10 to the minus 8. So by default, it takes more time and it is more accurate. I prefer it to be faster and a bit less accurate for this setting. Before calling the solve method, I'm taking the time, and then I'm taking it again right after, so that I can measure how much time it took for solving the problem. This is just out of curiosity. And here, basically, I'm doing the same thing I did before. I'm extracting the solution, so recovering the state trajectory, the control trajectory, and I'm also computing the joint torques for every time step, and the end effector position for every time step, because those are not decision variables of the problem, so I need to compute them after solving the problem. And this is just code for creating the viewer with the robots and visualizing the motion in the viewer, so that we see the motion of the robots. This is a function that does everything. And this is a connection to the viewer. So you can embed the viewer inside the notebook, so that you can see it directly here without opening a new tab. So this is the robot. And now I need to execute this. And now you have this widget here that I created, which will allow us to play a bit with the weights of the cost function. So I prefer to use the log of the weight, because I think it makes it a bit easier to play with. So -3, it means that this weight is 10 to the minus 3. Okay, look, I think it's easier to play with it in logarithmic scale. So at the moment, all the weights are set to 10 to the minus 3, and the robot is basically not moving, because I think we have way too high weights on the accelerations and the velocities, so they are too heavily penalized, and so the robot is not moving. So I would start by penalizing less the accelerations. You can see that as soon as you change the weight, the motion is recomputed and is played in the viewer. I would reduce also the penalty on the velocities, and you can see the robot is moving more and more. That red sphere over there represents the target, which should be reached with the end effector. So at the moment, it's not reached. Okay, I'm reducing the penalties on velocity and acceleration at the minimum. I'm also going to increase the final cost. Okay, so now you can see that the target has been almost reached with the end effector. I can make the final cost a bit larger. Okay, now you can see that the robot has really reached the target with the end effector. You can also add increase this one, so it's going to be reaching it faster because you have a higher penalty on the running cost on the desired end effector position. So it's going to try to reach it as fast as possible. So probably this is like the fastest it can reach it. And if you scroll down, you have a similar thing happening, but doing plots instead of showing the motion in the viewer. So we have the same widget, but every time you update the widgets, you get these plots updated. So these are the joint torques, the joint velocities, and the end effector position with the desired values in dotted lines. So we can try to do the same thing, like we reduce the penalties on the velocities and the penalties on the accelerations to the minimum. And now things are already going better. So the end effector is actually moving towards the target. We can increase the weight on the terminal position. And now we can see that finally the end effector actually has converged to the terminal desired state. But it only converges at the very end. If we wanted to converge faster, we need to increase also the weight on the running cost. See, now it has converged a bit faster, and if we keep increasing it, it converges even faster. So if you set it to the maximum value, then it converges in like 0.6 seconds, while it adds 1.5 seconds to complete the problem. This is what's going on for the joint velocities. You can clearly see that here there was a saturation. So the reason why it wasn't able to reach the target faster is that you had velocity saturation on many joints. Indeed, the joint velocity limits for these robots are, I think, set to pi, so 3.14, and you can see that you have several joints that are saturating the joint velocity limit. And here you can also clearly see that there was a saturation on the joint torques. When you see these kind of flat lines, typically those are the signs that there is a saturation going on. So the robot is at the beginning, it's accelerating as fast as it can by saturating the joint torques, but then it reaches the joint velocity limits for some joints, and so it can no longer accelerate because that would violate the joint velocity limits. So it remains at constant velocity for a while, and then it decelerates because when it reaches the target, it wants to stay there, so it needs to reach it with 0 velocity. Okay, I think we have been going on for a while, so we can take a break. You can play a bit with the notebook or with the scripts as you would like to get a bit acquainted with how it works. And then after the break, we can see how this is translated in single shooting. So I'll see you back here at 58. Okay, so let's move on with the shooting notebook. So you can open manipulator_shooting. The notebook is basically a copy paste of the previous one, so it contains the same introduction, which we don't need to go through because it's the same. So I'm just gonna skip past it. the problem is the same that we wanted to solve before. So the only difference is going to be in how we formalize the optimization problem, because now we want to use a single shooting approach. The first difference is going to be in how we define the decision variables of the problem, which is here. So this is the main difference. When you create the decision variables of the problem, now you don't want to have variables both for the state and the control, but you only want to have variables for the control. And you can see indeed the only place where I call the method opti.variable is here, when I create the control input variables. And then how do I compute the state? Because I will need the state for computing the cost function. So the way I compute the state is that I simply integrate the dynamics to compute the state as an expression. It's a function of the control inputs. So it's not directly a variable of my problem, but it's a function of my control inputs, which are the variables of my problem. So you can see here, I always have the list for the state x, and I initialize it with the initial state x init, which is simply a constant. And then inside this for loop, I compute x next by taking the last variable in my x list, and I sum to that dt times the evaluation of my dynamics. And then I add this variable to my list x. And since I'm there, I'm also specifying the state bounds based on this expression that I just computed. So it seems very similar to what we did before, but in terms of formulation of the problem is very different, because now the state is not a variable. It's an expression of the control inputs. So we're going to see that it's going to have a big effect on solving the problem. So when defining the running cost and dynamics, actually, I don't need to specify the dynamics, because the dynamics is automatically satisfied when you do single shooting, because the state is computed by using the dynamics, integrating it. So this function here is the same as we had before, but just we don't have the dynamics constraints. I removed those lines. But apart from that, everything looks the same. So this is my terminal cost, same as before. Again, this function here is the same as before. Extracting the solution the same way I did before. Creating the viewer and visualizing the motion in the viewer, same as before. So nothing has changed. I forgot to execute stuff, so I'm gonna just run all. So now it's solving the problem, and when it's done solving, it's gonna visualize everything in the viewer. So as before, the robot has moved very little, because the way it's on the position, sorry, on the velocity and acceleration terms are too large. But look at that. So solver time, 12 seconds. So now every time you move a weight in the widget, you will need to wait roughly 12 seconds to get a solution. if we go here in the previous script, solver time 0.8 seconds. So there is a huge difference in how much time the solver took for solving the problem. So this might be even counterintuitive, because with single shooting we said we have fewer variables, fewer constraints, because we have removed the state from the variables and we have removed the dynamics from the constraints. But the problem is that now we have an optimization problem which is dense, and it's actually very complex in terms of the mathematical expressions that needs to be evaluated and differentiated. And so even if the problem is smaller, it takes much longer to solve. The solution is probably the same or very similar in this case. So we don't have numerical problems, but it's just much slower. Takes roughly 10 times longer. You can see we are slowly getting there. I need to get to -6, and then I need to increase a bit also this. Well, it's a pain to stay there and wait. But you can trust me, eventually you're gonna get the same behavior that we were able to get with collocation. So you need to be very careful when you formulate your trajectory optimization problem, because you can see that even a very small difference in the choice of which variables you decide to use, which constraints you decide to use, can have a large impact on the solver time. Yeah, so it's getting there. We are able to get a solution that makes the robot reach the target. Well, this time it took 15 seconds, so it's even slower. So we have another 15-20 minutes together. I suggest we use this time to play a bit with the script, and maybe I stay here just in case you want to ask questions or you need to solve some problems with the software, because I finished everything I wanted to show you today. So rather than starting something new so late in the lecture, I think it's better if you just play a bit with the code. And well, after here you have the same code as before for doing the plots. I'm not gonna use it now because every time I change something, I have to wait 12 seconds, so it's too slow. Okay, you can play with the codes, and if you need anything, I'm here.